all of them from Politecnico di Torino. In this work, what we aimed was to extend the well-known finite fracture mechanics failure criterion for its use in dynamic loading conditions. In this sense, we can study the following problem, in which we have a structural domain filled with a homogeneous, isotropic, linear elastic, and brittle material that is subjected to dynamic loading and boundary conditions. And this domain has, let's say, a special feature, a stress razor, so that it can be a notch, crack, a hole, a void, whatever. But so that we know that failure will stem from this stress razor, and we know the stress field, the dynamic stress field before crack propagation, and the energy release, the dynamic energy release, once the crack has propagated. In this situation, we would like to have some kind of a failure criterion in order to assess when will this structural domain will fail. However, there are some, let's say, some proposals in the literature. However, before we go, I present those. I would like you to, I would like you to know, to be aware of some of the requirements that any dynamic failure criterion must comply in order to be, for it to be robust. The first one is, let's say, the easiest and most obvious one is that obviously any dynamic failure criterion should be applicable to quasi-static failure conditions, because it's just a particular case of the latter. Another one is that every proper dynamic failure criterion should be based upon non-local and non-instantaneous conditions. This basically arises from the conservation of momentum. Otherwise, we are, let's say, breaching one of the basic rules of physics. And so this is, let's say, one requirement. In my opinion, this introduces a very beautiful symmetry, spatial-temporal symmetry, so that whenever the stress gradient of the stress field with respect to temporal or spatial coordinates is non-zero, we are not allowed to use point-wise conditions for predicting failure. What's more, is that actually almost every failure criterion is based upon a minimization problem. And in quasi-static scenarios, normally we use a minimization in terms of the applied load. However, since a failure is an irreversible phenomenon, we should apply it in terms of the time to fracture. Okay, however, I will make a remark about this afterwards. But yeah, basically, failure must occur at the first instant in which the necessary conditions for failure are met. And obviously, as the rest of failure criteria, it should be able to explain the experimentally observed phenomena. For example, the apparent strengthening or tautering of the materials with increasing loading rates, the propagation of the crack after the peak loading is reached when we are using short pulse loadings, or for example, in quasi-brittle materials, there was shown in the literature that above a certain critical loading rate, there is a complete switch in the failure regime on the materials. Okay? So, having those considerations in mind, I will now present some of the existing failure criteria that have been already proposed in the literature from a very long time ago. The first one was the classical approach, which is, let's say, the easiest one. Basically, it's based upon local and instantaneous conditions, either on the stress or on the stress intensity factor, depending whether it's a singular or non-singular geometry. And basically, we compare either the stress or the stress intensity factor with some critical values that depend directly on the fracture toughness. However, we see that still we have no local and instantaneous, so that's bad according to what I said before. And also, before being able to apply these criteria, we need to find these master curves of the dynamic loading, of the dependence with the dynamic loading. What's more, after that, we can, let's say, further develop the model and introduce what it says the dynamic extension of theoretical distances. In this sense, basically, what we do is we perform a non-local computation of the stress, and we compare this non-local stress with a critical value that once again depends on the loading rate. So we solve one problem, but on the other hand, we introduce one more problem, is that we are using a constant characteristic length, which is this d, and so we are precluding the use of this criteria when the specimens are short, like in the order of d, which is, for example, very bad for rocks or for metals that whose let's say characteristic length is quite large. And the last case, okay, if it's appear, is the incubation time failure criterion proposed by Petrov and Morozov almost 30 years ago, in which basically we keep solving some of the problems. So now we have a non-local and non-instantaneous criterion. We no longer are required to find this relation between the strength and the loading rate, because we are introducing here this parameter Chao, which basically performs an average of the solicitation of the solid. So it's one extra material property, or one extra property at least. But still we are using this constant characteristic length, so we are having the same problem as before. And this is basically where we are trying to implement and to improve our proposal, no? for improving this issue. And so now I am in the position to present you my dynamic finite fractal mechanics proposal. Okay. For doing that, first let me assume the following hypothesis. The first one basically introduce what it states is that the dynamic loading starts at t equal to 0. Okay, this is just for convention. And the second one is that there exists an explicit one-to-one relation between the dynamic loading, the dynamic stress field, and the dynamic energy release. And all the temporal dependence of the latter arises from this part, okay, from the dynamic loading. We will see then that actually, even though it might seem a bit restrictive, we will see that in many cases we can still use this, we can still have these hypotheses. Under those conditions, basically, we can assume that failure will happen at the first instant that complies with a series of let's say necessary conditions for failure, which are as follows. So basically, we can see here the minimization problem subjected to some conditions. For those of you who are already aware of finite fractal mechanics, this is very similar, okay, to, let's say, the average stress condition proposed by Cornetti in 2006, whereas the second one is, let's say, basically the energy condition. The only difference is that instead of assessing these conditions in an instantaneous fashion, like in the quasi-static case, we are introducing here an effective measure of the dynamic loading, so that it's no longer sufficient to meet these conditions at an instant, but we should meet these conditions through a certain period of time, which is governed by this tau, which we will call afterwards the coalescence period, which is something analogous to the incubation time of the Petrov's theory. Okay. Now, with this theory, we can do some remarks. Okay. The first one is that obviously this minimization over time reverts to minimization over load whenever the loading is monotonically increasing, which is something that in the quasi-static setup is, let's say, an undercover assumption that we always use. Then, obviously, the integral over time of this dynamic loading is performed in the past and not in the future, because otherwise it would be meaningless. This coalescence period here will be assumed as a material property. However, this is something that is still to be further assessed because we need more experimental evidences. The interpretation of this coalescence period, as its name already infers, is that it is the minimum time required for the material to coalesce the most unfavorable macrocracks into a single macrocrack, so that failure occurs as a fracture surface. Okay. However, we are not imposing that failure should happen always in a period of time larger than tau. But in the otherwise, what it will happen is that we are expecting failure to be more diffused into the damage, or into the domain, instead of just in a clean fracture surface, let's say. And lastly, obviously, there is some kinetic energy component that will affect both the stress field and the energy release rate, okay? Like in the generic scenario. However, under some conditions, as was proven by this work by Dai et al. In 2008-2010 and Fu et al. In 2002, using the split Hawkinson bar system and a proper pool shaping technique, we can have the following, so that we can have dynamic equilibrium conditions in the specimen. And what's more, we can have that the static expressions relating the load, the stress field, and the energy release rate are still hold during the dynamic regime. This is of huge importance for this work, because it allows us to get the program I presented before, make it static, perform some static finite element analysis, get the stress field and the energy release rate, Now, just by substituting this load by the actual dynamic load, we have the dynamic magnitudes. Using the dynamic finite fracture mechanics proposal, we can get the failure conditions. We should be here. Okay. We get the failure conditions, so we get the time to failure, the instant failure load, and this, let's say, length, which is similar to what's the length in the quasi-static case. Okay, so now that I have presented that, I will do the particularization. In this case, for a symmetrical bend test, this is based on some works in rocks in Laurentian granite from the literature. Okay, here we will consider both cases, so notch and un-notch symmetrical bend test, so singular and non-singular geometries. From finite element analysis, we can get both the stress field and the stress intensity factor. The experiments were like can be, let's say, the loading profile could be modeled as a ramp loading, so as it is in the picture. Obviously, we have a piecewise definition of the loading, so we will have also a piecewise definition of the fracture load. Now we introduce everything in the formulation. Basically, since we have a monotonically increasing load, we have a positive geometry, so on and so forth. We have the condition minimization problem reversed to the resolution of a system of equations with two unknowns, from which we can get the failure load. So, as I said, always is piecewise because for low loading rates, we have time to failure larger than this coalescence period. And basically, we have this the quasi-static solution plus a linear term depending on the loading rate. As we keep increasing the loading rate, we will have another solution. So, and now what will happen is that when we are computing this integral, we will have a part which is in the loading part and another part which would be before starting. And this is just the square root of the quasi-static solution multiplied by the square root of the load. And now if we go to see the experimental results, we see that for the notch symmetrical bend test, we have a very, very good fitting, okay? Whereas if we go to the un-notch symmetrical bend test, we have a very good fitting at the beginning, but as we keep increasing the loading rate, we start having a bit more of a difference. Actually, we found that this is due to the fracture pattern, so we see that for reasonably low loading rates, we still have a fracture surface. However, as we kept increasing this, it would diffuse into this domain, and so we are somehow under-predicting the release of energy upon propagation. Okay? So basically, with that, I can conclude my talk. So basically, we presented this dynamic finite fracture mechanics proposal that has a very good agreement with experiments. Okay, we are able now to explain why is these differences in the loading, in the failure patterns with the loading rates. Also, it's very important to acknowledge that the use of indirect tensile specimens for hugely simplifies the dynamic testing using the split Hawkinson bar system. And lastly, that obviously we are in urgent need, let's say, of further experimental campaigns in order to further test our theory and in order to get to be able to assess better the quality of our results. And that's it. I would like just to thank the New FRAC Consortium and also the funding received from the European Union. And thank you so much for.
Yes, please. Could you please comment about the explicit magnitude of your coalescence time?
Of the coalescence time, yeah, it's for this case.